All right, let's look at another pretty interesting thing. I think this one is very cool. Midline quadrilateral. The following investigation leads to, I think, a very interesting result about the properties of a midline quadrilateral, giving any quadrilateral to start with. By this time, hopefully you know the drill. I'm expecting you to work through the following tasks before reading on in the text or watching the rest of the video. So here's the task in GeoGebra. Construct a general quadrilateral ABCD. Construct the midpoints of each side and construct the midline quadrilateral. And here's the question: what type of quadrilateral is the midline quadrilateral? Might surprise you. Move the vertices around. Is there, it's just starting with any quadrilateral. So do you just get any kind of quadrilateral for the midline quadrilateral, or does it have to be some special kind? When you think you have an answer, test out your conjecture by manipulating the vertices. Does it still work in all cases? Try some concave ones, some convex original quadrilaterals. Just check it out and see what happens. Now, construct one of the diagonals and then see if you can prove your conjecture. And hint, the diagonal is going to be helpful. Consider some triangles formed by the sides, the midlines, and the diagonal. And you might use a theorem that we've looked at here in these playlists here just a video or two back. And that midline triangle theorem is going to be pretty helpful here. So go ahead and work this out on your own. Come back when you've done this. Press pause now. Well, if you did this yourself, you constructed a general triangle like this. You made the midpoints of the sides and then the midlines. What shape does that look like? Well, sometimes it's a rectangle. Okay, well, it looks like it's always a what? Looks like a parallelogram. Even when it's convex, even when it's not even simple, it even works. It looks like it stays a parallelogram. So look at one of the diagonals and see if you can prove it's a parallelogram. If you haven't done the proof yet, here's a hint. I want you to think about it a little bit more before you keep going. Look at this triangle here, ABC. This is a midline of that triangle. And what do we know about this line, midline, versus this side of the triangle, which is a diagonal to our quadrilateral? And then what about on this side? How does that one compare to that? What does that say about how these two compare? And what does that say about the original figure? See if you can write out the details of that proof before you see me do it. Press pause again. Okay, well, here's the proof. So given any quadrilateral ABC, D, construct the midpoints W, X, Y, and Z of sides AB, BC, CD, and DA, respectively. Construct diagonal AC and midlines WX, WY, YZ, and ZW. Is that right? WX, XY, and ZW, I should say. And note that by definition, WX is a midline of triangle ABC. By the triangle midline theorem, we know that it's parallel and half the length of the other side, which is our diagonal AC. So WX, that distance, is 1/2 the distance AC. Similarly, YZ is a midline of the triangle over here, triangle ADC. And so it's going to also be half as long and parallel to this. Well, parallel lines are transitive. It forms an equivalence class. So, if this line is parallel, if these two WX and CA are parallel, and this one's W or ZY is parallel to CA, then these two sides of our median or midline quadrilateral are parallel, and they're also we decided they're both 1/2 the length of AC. So in length, so that means they're the same length and parallel. Well, think about the properties of a parallelogram that we proved in the parallelogram theorem. This is sufficient enough to conclude that the quadrilateral WXYZ is a parallelogram. Isn't that pretty cool? Doesn't matter what kind of quadrilateral you start with, you always get a parallelogram when you connect up the midpoints. I think that's awesome.